Hello, everybody. Thank you for joining us, as always. Welcome. It's good to see folks saying hi in the chat. Nice to see some familiar faces or names there. Feel free to say hi. If you're new, of course, as always, please let us know where you're from and say hello as well. I have a question for you in the meantime, especially if you are a repeat guest. What are the big picture habits, good habits for how to solve problems with computers that you feel like you have learned since we got started? So we've been doing this for a number of sessions now. We're like nearly 3 months worth of streams on how to effectively program. What are the big picture habits that we feel like we've hopefully not bad habits, but good programming practices that we've acquired as we've gone? Ben, welcome. Thanks for joining us. Sounds like you nearly have every region of America covered. Good job there. North Carolina, obviously the best place you've lived. Roy, use it every day. I like that. How about in terms of like actionable things? Things that we have put into practice. Not a modular programming in OOP. Good. Okay. Two different topics there, but I like that. Yeah, modularity's been a huge part of what we've seen. AKB, good. Make functions small and delegate to subroutines. Iris, thank you. Top-down design, bottom-up implement, all great. All excellent. There's one thing in particular that today is going to be about. It's going to come back to. It's because what we're going to start tonight's stream with is probably the best example of all of something that we have seen throughout our course. As when you said doc strings and algorithm logic, yeah, if you're not comfortable with the logic of algorithms, it doesn't matter that AI can generate code. It's always really important to understand algorithms from the perspective of seeing how they're implemented. I think that's really useful. You can, of course, study algorithms with pencil and paper and just understand them on a high level, but a lot of times that's as hard or harder than trying to appreciate them by getting your hands dirty and actually implementing them. All good. There's one thing that we're going to see heavily today, and it's related to these ideas of modularity, making your functions small, and using subroutines wherever possible. Delegation is probably the most important word that we're going to touch on at the start of what we have today. So this idea of delegation to subroutines. And we're going to get into recursion. And another way that we have introduced this idea of delegation is via, in the chat we had a great way of defining it a few sessions ago, which is structured procrastination, right? We are going to be lazy, but we're going to be lazy in ways that are very intentional. And so to that point, we will use recursion as a warm-up to come back and finish our implementation that we have of UPGMA. And it's a really exciting type of session because we get to apply UPGMA after we see this very fundamental concept in programming that maybe a lot of courses would have covered already. We're covering it kind of at the end of object-oriented programming. But we're going to get to see how recursion is useful and this concept of delaying our and delegating and procrastinating and being lazy, all that's going to be heavily involved with recursion, and that will finish up our evolutionary tree construction algorithm, and then we're going to apply it to some real data sets. So we have a data folder that actually has quite a few folders inside of it, and I'm going to tell like a few different stories, and that's nice because we'll also get to visualize the trees. So we're not just going to make the trees tonight. We're also going to take a look at the trees, and we're going to tell real biological stories by generating an evolutionary tree. So we've seen a lot of visual demos, especially as we're able to do more advanced stuff. And this visual demo is not as like beautiful maybe on a visual level as some of the stuff we've done either on the practice side with the Boyd's algorithm or the Gray-Scott simulation. We also we have a homework now out that's all about scaling up our gravity simulator to be able to visualize the collision of galaxies. And so we can simulate like 2,000 stars at a time. And it's all built on what we're doing here with evolutionary trees. It's probably my favorite homework because it's a physics problem, but using a tree, and it's the exact same thing that we're looking at here. And until I started looking for it, I had never heard of this algorithm. It's called Barnes Hut. It's an amazing homework assignment. So enjoy like taking the time to do that in our practice exercises, because we built out a lot of autograders to check your work on that. And it's a complicated assignment if you had to program the whole thing. But when you're on Rails a little bit, you have these autograders. It's just a fantastic assignment. All that being said, putting together all these examples was a huge amount of fun. And so is it going to be as visually appealing as that? No, we're going to be making trees in R. But we're also going to be able to tell like genuine biological stories. And 3 of these come from impactful papers in biology. And it's cool that we live in a time where we can just replicate this work that at one point in time was like a frontier result. And UPGMA is going to be enough to answer all of these questions for us. So we'll place ourselves in the shoes of people doing real work once they had better molecular data. And that's how we'll kind of wrap things up. I did mention R, so if you want to follow along, notice that we have a visualize trees.r file. I have added that to our starter code. So let me drop a link to that starter code in the chat. And I also, if you have already downloaded the starter code from when we did our first stream on this, then you're going to notice the data I've made them a little richer, meaning that I got larger data sets and I generated distance matrices that were more accurate, like using better algorithms. So that's a topic that we're going to come back to, but you can grab updated data as well as this R pipeline in that folder that we have on our starter code. So we'll see some beautiful real results. We're going to finish up our evolutionary trees algorithm, finish up object-oriented programming today. It's going to prepare us for the next topic that we're going to see. The next thing that we're going to do is on parallel and distributed algorithms. It's a particular point of pride because I am not aware, at least at one point in time I was aware of the fact that there were no introductory programming courses out there that teach parallel programming and distributed programming, meaning taking a task and dividing it over multiple computers. This is a way of life today. This is powering the AI revolution. And it's also something that we have built into Python, and we can build a real scientific demo that's all around how is it that we take a task that we want to perform and split it over a bunch of computers that can coordinate their work. So that's what we'll see next time. For now, we're going to finish up object-oriented programming, and I think we're ready to get started. So if you haven't already, of course, please subscribe to us, like this video, join our mailing list on Discord. I mentioned that we have practice exercises accompanying this on the Barnes Hut algorithm. We also are about to announce some Part 2 projects, as well as a new cohort of projects accompanying Part 1 of Programming for Lovers. So The way to unlock those is to join our Philomath subscription. And so wherever you are, if you're still kind of finishing up part 1, we have a project that's on everything up to object-oriented programming. And then we're about to launch some part 2 projects. So if you want to do more with object-oriented programming, more with parallel programming, which we're going to start learning about, there's going to be an opportunity to kick that off in about a month or so. So that's all in terms of like general announcements. As always, thank you for joining me. This is some of my best times of the week. I can't wait to show you some of these demos. So even if you find what we do with recursion and coming back to finish UPGMA, even if that's challenging, you can always watch this back, but you will, I think, really appreciate what we're going to do in terms of the biological stories that we get to tell. So we're ready to get started. I'm going to move us over in this file explorer to not look at UPGMA because we're going to take a little bit of a step back and look at a little about recursion. So that's where we're going to start, and I think we're ready to get started. As always, if you have any questions, let me know in the chat. You said there's no R in the file from the link. I think there should be. If there's not, like, imminently, well, I'll just make sure to add that when we're finished here. So I just got to compress everything to a zip and get it added over. All right. So we're going to start with a recursion folder in our SRC directory, and we have a main.py file that just has some starter code here that's around recursion. A long time ago, we introduced a problem that was all about summing the first n integers. So we've come a long way. If you've made it this far, starting all the way at the beginning of the course, then you will have seen towards the start of the course when we were first introducing loops and control flow, one of the problems that we looked at was a function that was about, say, summing the first n integers, where I took an integer n as input, and I returned an integer as a result. So that function, I'm just going to give it a very short doc string to say it returns the sum of the first n positive integers. And of course, we learned things like if n is less than 0, this doesn't make a whole lot of sense. So we're going to raise a value error, and that value error is going to say, input cannot be negative. If you've been with us for this whole time, and you remember when we wrote this function using a for loop or using a while loop, and that was somewhat new, congratulations. I think it's an opportunity to pause just for a moment, take a deep breath, reflect on the journey we've taken, reflect on how far we've come now that we're working with object-oriented programming. Now, though, I'm going to show a slightly different solution here. And now, the sum of these first n integers, Gauss would say, it's just n times n plus 1 over 2. We don't even need a loop in order to compute this. But that's math. That's hard. And I'm going to show a solution to this with a third approach. So we've seen how to solve this using a loop. Gauss gave us a precise closed form formula that just says, well, multiply those two numbers and divide by 2. But we're going to show a way that is based off of recursion. So say, for example, again, because I'm not good at math, say I was presented with Gauss's quandary. Say in some particular case, I was asked to sum the first, let's say, 50 positive integers. And we didn't know this formula. Well, if that were the case, one of the things that I might do is to say, I'm bad at arithmetic. So maybe I'll just remember the number 50, and then I'm going to ask someone in the chat to give me the sum of the first 49 positive integers. So whatever you tell me, I'm going to just add 50 to it at the end. And you say, well, I'm not good at arithmetic either, so I'll just remember the number 49, but I'm going to delegate the sum of the first 48 integers to another friend. So in this particular case, what we're seeing is the idea here is, remember n and aggressively delegate the sum of the first n minus 1 integers to a minion. This is a simplification of the idea of recursion, but I think it's a really good one. The only problem, though, is that a lot of the time when we've been writing functions and we want to have this notion of structured procrastination or laziness, and we want to make sure that we're always handing stuff off to a subroutine, well, that subroutine was another function. But in this case, the sum of the first n minus 1 integers is going to be myself. In some sense, I am the subroutine that I would be calling in this case. And so here, we're going to represent this idea of pulling off just the n and handing the sum of the first n minus 1 integers as a delegation, as acknowledging that, well, I have to call myself as a subroutine. So this process is going to continue. And this process would continue if you continue our analogy from before of thinking about this happening in a human chain. I'm remembering 50, you're remembering 49, your friend is remembering 48, and there's a chain of 50 people involved, until eventually the 50th friend just says, well, the 49th friend says to the 50th friend, what is the sum of the first one positive integer? And I'm going to remember 2, and I'm going to add 1 to that. And when you get to that point, then in that particular case, that person simply is going to return 1. When they return 1, the person who asked them will say, oh, I just need to add 2 to that. And so they tell 3 to their own friend, and the friend was remembering 3 plus whatever their friend said, now it's 6. And so we're working our way back up the chain until I receive whatever the sum of the first 49 integers is from you, and then I just add 50 to it. So the chain works its way down, and then it works its way back up. I could show this, in fact. I have it, I think, in the UPGMA folder. I have an illustration of this process. Oh, and I need to save it without a background. So this is perhaps not the prettiest, but perhaps you can see anyway. So it's a transparent background, so VS Code has given it not the most attractive look. But the idea is we're going to have a recursive sum. This is the function that I'm currently writing. If I called it on an input value of 6, it would try to return 6 plus the recursive sum of 5, but we have to wait on recursive sum of 5 to finish. And so this process carries on down the line until we hit something like recursive sum of 1, and that becomes equal to 1. When that happens, and these arrows are not the easiest to see, that value of 1 gets returned into recursive sum of 2 because it was waiting on recursive sum of 1 to finish. Recursive sum of 3 was waiting on recursive sum of 2 to finish, and so on. So this 3 goes into recursive sum of 2 here. This 6 goes into what recursive sum of 3 was here. This 10 goes into what recursive sum of 4 was here, and this 15 goes into what recursive sum of 5 was. So at the end of the day, we return 6 plus 5 equals 21. That whole idea can be represented very simply by saying, every recursive algorithm has sort of 2 cases. The easiest case is to be the last minion. So if you're the last friend asked, and you were given an input value equal to 1, then you would simply return 1. And I could be very precise and say, you know what, well, if n is equal to 0 or n is equal to 1. Let's make sure that I handle any possible input. I don't want to return a value error if n is equal to 0. Then in this particular case, I'm going to return 0. And if n is equal to 1, I'm going to return 1. Okay. Boy, that was messy. The remaining cases are where the delegation happens. Okay. Except the delegation is to myself in a sense. And so the inductive step, and this easiest case is called the base case. So the remaining part of the algorithm is this inductive step, and it applies a recurrence relation. What is that? It's a formula for something in terms of smaller inputs to the function. Okay. So in this particular case, the formula that we care about is that the sum of the first n integers is equal to n plus the sum of the first n minus 1 positive integers. And so in this case, here is where I get to apply my laziness. And if I have reached this part of the function, well, I know that it's not the case that n is less than 0 because I would have already produced an error. And it's not the case that n is equal to 0 or 1 because I already would have returned a value in either of these base cases. But what is true is that I know that n is greater than 1. And if n is greater than 1, here's where I'm going to say, you know what, that's too much math for me. Instead, I'm simply going to return n plus the sum of integers of n minus 1. And this is a function call that is recursive, meaning calling itself, because the function that I'm in is some integers. This might look a little strange, but it's a feature that every modern programming language will have built in because it's a nice way of writing functions. And in this case, there is a shorter way of writing the function that is not recursive and that doesn't even require a loop, but that it just has our closed formula. What we are going to see is that there are some circumstances where using a recursive function is actually the best imaginable way of solving the problem, because there are certain types of problems, and we're going to see this in the context of evolutionary trees, where solving the problem recursively makes solving that problem much easier. So in the meantime, I'm going to take a look at another example. We could, for example, do the same sort of thing with a recursive factorial function that also takes an integer n as input and produces an input as output, an integer as output. So in this particular case, we're going to return n factorial for a given integer n as input. We can do the same thing. If n is negative, then we of course want a value error and say that we were given a negative input. If we make it here so you could imagine there is an else, but we don't need an else if in this particular case we've already raised an error. So in this case, I don't even need an else, but I can say return, well, if it's the case that n is equal to 0, then in that particular case, I'm going to return 1. So we're saying 0 factorial is equal to 1. 1 factorial is also equal to 1. So you might want to say, well, in this case, if n is 0 or n is equal to 1, we return 1. You don't need to do that, but I think that that's very intuitive. And then if we make it here, we know that n is greater than 2. So we've handled, in this case, our base case. And then for the inductive step, we remember here that n factorial is equal to n times n minus 1 times n minus 2 times, and so on, all the way down to times 2 times 1. And there is a recurrence relation here that's saying, well, if I want to multiply the first n positive integers, it's n times the resulting product of everything else, which is just the product of the first n minus 1 positive integers. So here's where we're going to have n minus 1 factorial. So once again, we have this recurrence relation, and that's going to allow us to apply the inductive step here and say, if I've made it here, I know that n is greater than 2, or greater than or equal to 2, I should say. And so I can return n times factorial of n minus 1. Let's do one more just to practice. We've seen Fibonacci numbers going back to the long ago of the introduction of our course, where we'll take an integer and return an integer. So returns the nth Fibonacci number, where the sequence is given as 1, 1, 2, 3, 5, 8, 13, etc. Each number is the sum of the, did not mean to run anything here, previous two terms. And the first two terms are 1. So we'll do this as a zero indexed example. And in this particular case, well, that means the first two terms are both equal to 1. So if n is greater than less than 0, I'm going to raise a value error and say negative input. But if I make it to n being equal to 0 or n equal to 1, and here's where I was preparing you a little bit to think about a base case that has more than one possible value. So if I'm looking for the nth Fibonacci number, this would be n equals 0, this would be n equal to 1. In either of those cases, well, I want to return 1. So here is our base case. And then we have the recursive part of the algorithm, the inductive step. For the inductive step, well, we know that f of n, the nth Fibonacci number, is just the sum of the previous two. So that's f of n minus 1 plus f of n minus 2. And so if I'm here, I know that I can safely say, let's return that sum. All this is good. We should just make sure our functions are working. So we should take a look at some integers, factorial, and Fibonacci, and just plug in a few values. So we can look in main and say, let's try printing sum of first 50 integers is, and let's call sum integers of 50. And we can run that one and test it first. So I'm in SRC, which means I need to cd into recursion. And then I need to Python 3 main.py, or Python if I'm on a Windows machine, of course. So I'm going to say the sum of the first 50 integers is 1,275. In honor of Gauss, we should probably do 100, because as we saw a long time ago, that's a special value. It's 5,050. And everything looks good here. So we're going to print, we don't want to print a huge factorial because they're going to grow pretty fast. But let's just say, 10 factorial is, and here's factorial of 10. $3,628,800. I buy that. And finally, we're going to print, let's say the 8th Fibonacci number is, and Fibonacci, if I want to be really precise, Fibonacci number at index 8 of the sequence, because we're starting to count this as a zero-based indexing. So let's say Fibonacci of 8, and run that. And that tells us it's 34. So maybe we want to print a value that we know of. This is 0, 1, 2, 3, 4, 5, 6. So I'll just say this next value is 21, and then it's 34. So that indeed matches what we would hope. And everything is working well so far. Of course, the thing I might be curious about is it would become tedious to compute these Fibonacci numbers by hand. So let's say the Fibonacci number at index, let's say 100 of the sequence is, and now I'm going to compute Fibonacci of 100. So we're going to run that, of course. And we see that the Fibonacci number at index 8 is 34, but we haven't actually printed the one at index equal to 100. Now there's something wrong. The question is, what did we do bad? We did something bad. Does anybody know what it is? This is a good plug for this series that we're also doing on Roslyn problems that we're doing on Thursday mornings, because we already saw this exact same story in that sequence. So if you happen to be following that series, you would know the answer there. Did I define n equal to 1? I think I did. Yeah, that's one of our base cases. AKB says we are recalculating prior values multiple times in the algorithm. All right, I like that. So what does that mean? So if we take a look at our Explorer, then I have a figure to show this. And remembers what this is called. Or Remy is able to identify what the name of this figure is in the output that, or in the folder that we have. So either way, the answer is right, which is that I call this big tree bad. It's because I've taught this a fair number of times to students, and I've always asked for an explanation as to what exactly is going on, because we're going to have to control C this process. It's never going to finish. And the best answer I've ever had was from a student who said just 3 words, big tree bad. And the reason why big tree bad is that if we were computing fib of 7, and this is a figure showing the circumstance where things are 1 indexed, so we're not going to consider fib of 0. So in this case, fib of 1 and fib of 2 would both be equal to 1. Those are the first 2 elements in our sequence. But if I were computing the 7th Fibonacci number, which you already know, that 7th Fibonacci number, which would be the one at index 6, is equal to 13. So that's not a complicated value to compute. We would say 1, 1, 2, 3, and we just add subsequent values. However, if we try to do this recursively, then what happens is when we call fib of 7, well, it calls Fibonacci of 6 and Fibonacci of 5 and tries to add them after they have completed. So we're waiting. We did our aggressive, lazy delegation, and we passed off the work to Fibonacci of 6 and Fibonacci of 5. And each of them passed on the work to 2 other minions. The problem is that before, when we looked at our recursive sum or factorial, we were only delegating the work to 1 subroutine. And every time we reduced the size of the input by 1. So if we were calling recursive sum of 100, then we only need to make 100 function calls. The issue here is there are a couple of things. Number 1, we're only decreasing by 1 or 2 in terms of the input, and yet we're making 2 function calls each time we go down. The bigger problem is not that we have necessarily only that we have this branching in our function calls. The bigger problem is that when Fibonacci of 5 tries to delegate its work to two minions, Fibonacci of 4 and Fibonacci of 3, this function call to Fibonacci of 3, for example, is also going to get called by Fibonacci of 4 here, and it's also going to get picked up here, and it's also going to get picked up at this part of the tree, and it's also going to get picked up at this part of the tree. So none of these individual function calls are aware of the other. These are just the result of delegation that's happening at different points of the tree within different chains of function calls and subroutines. As a result, you can see that this tree is growing kind of, sort of, like 2 to the n. And when I was trying to compute Fibonacci of 100, it was creating this enormous tree of size that's, I think, generally proportional to 2 to the 100, which is not something that we really, in general, want to be in the business of, especially given that if you wanted to compute the 100th Fibonacci number, it's just a matter of making 100 additions. So you do 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So you just have to do this 100 times. So that's not a hard task to a computer. I'll leave it to you to fix this if you haven't done so already, because this was one of our exercises moving back towards the very start. Our initial chapter of our course asked you to compute the nth Fibonacci number. So it's a very doable challenge, but if we try to use this version of recursion to solve the question, then we're going to hit what's called stack overflow, because all of these function calls are going to accumulate, and we're going to be waiting on functions to finish in the same way that you were waiting on your friend to you've just got to tell me what the sum of the first 48 positive integers is. But unfortunately, in this case, there are so many function calls that are sitting around waiting that it exhausts the amount of memory that you have devoted to it. In my case, I'm surprised that I was even able to run the function for as long as I did before I had to shut it down. That's it for just our initial introduction to recursion. The question is, how is it that we're going to take that idea and bring it back to our work with UPGMA? So here, for example, is a sample tree that we have to represent a small tree with 3 leaves in it that we're assuming came as the result of our UPGMA algorithm. So A and B have age is equal to 0, C has age equal to 0, the internal node here has age equal to 3. That means that these two edges are going to have weights equal to 3. The root has age equal to 4, so this edge here has a value equal to, or a weight equal to 4, because this is 4 minus 0. And this edge weight here is 1 because that's 4 minus 3. So we have a simple demo tree here to show UPGMA. We're going to come back to this and talk a little bit more about how is it we resolve a few questions that we had, in particular one function. Before I do that, I'm going to make sure that if you want to follow the work that we do, it sounds like R was not added to the starter code, so some folks tried to download it. So I'm just going to take like a minute or two, talk amongst yourselves. I'm just going to make sure that you have access to that. So really, if you're following this live, the last thing I want you to do is not be able to do the demo with me. So let me get that for you. Javier, welcome. Thanks for stopping in. All right, so I've updated the starter code now. That link I sent previously should be good. You might need a hard refresh or using a different browser or something like that. But I don't want to continue. I'm going to resolve the UPGMA story. We don't actually have that much code to write, and a lot of this is just going to be taking a look at some pretty pictures. So give that a try. Give me a thumbs up if you get the R file there. And as I said, you've got some updated data as well. Yeah, Ben, we also have suggestions on the best way to install Python. I don't know if it's the best way, but it's a way to make sure that it works until you become very, very capable. It's all you need. So check that out on our programmingforlovers.com website. It's like the first Python code along. All right. I think it's there. I thought it was there before, but I'm pretty sure it's there now. I'm seeing it on my end. So I'm going to return to UPGMA. We've got a sample tree here. The idea of what we're going to do is, well, let me bring up data types. Okay. So to come back to UPGMA, we've already seen recursion with UPGMA a little bit already. You weren't thinking about it, maybe in this way. But what we did was we established every node has a label and an age, but instead of explicitly having a collection of edges, we're going to represent edges as references within a node to two children. So I'm going to have my child 1 node, and I'm going to have a child 2 node. So that's how I'm going to represent edges. Now, this in essence is a recursive way of defining the node class that we have established. And we saw that this becomes tricky. So Python won't let us do what we would like to do, which is just to say child 1 is a node. We technically have to establish that child 1 is a node, and its default value can't just be none because, well, it's going to let you get away with this, but this doesn't make any sense because none is not a value that can get assigned to a node. It's just none. And so sometimes it's going to start off with a child. Sometimes it's going to start off without a child. And if it's the case that it doesn't, its value is going to start off with this value of none. Sometimes it's going to have a node associated with it. So this is also recursive. Where we left off previously was we wanted to write a method called countLeaves. And remember that in Python, when you write a method, meaning a function that I'm going to be calling with whatever the name of that node is, .countLeaves, you have this special variable called self, and self winds up as input to the function. This is not how a lot of programming languages do it, but it's reasonable in Python, and it's something that you can get used to. So what countLeaves does, and previously we wrote all of these functions to implement UPGMA, and it's the one function that was left. So our highest level function for UPGMA said, I'm going to take a distance matrix, which is just a two-dimensional list of floats, and I'm going to take a collection of species names representing, the names of the species that I assign to the leaves of the tree. So what are the rows of this distance matrix? what are the species that get assigned to each row. And we built an entire tree out of this. And we're thinking of a tree as just its collection of nodes. And the one function that was missing, because we didn't really have a good way of writing it, was in data types, this count leaves function. What's nice about the fact that a node is defined inherently recursively, meaning the edge relationships are getting stored as a reference to child 1 and a reference to child 2, both of which most of the time should be nodes unless we're at a leaf. Because of that recursive structure, it means that there are a lot of questions that you might answer or functions you could write involving trees where you can just write recursive functions to help you. I'll show you what I mean. So in this particular case, if we want to figure out how many leaves are there in the tree whose root is the current node. So if I'm at a particular node, how many leaf nodes are there beneath me? And I could look at my example tree and say, well, the answer here is going to be different depending on where I am. If I'm at the root, then the answer would be 3. A, B, and C are all beneath me. If I'm at this node, well, how many leaves are beneath me? Just A and B. And the other possibility is that I'm at a leaf. So if I'm at a leaf, well, the answer here is always going to be 1. We're headed then towards an idea for how we might answer this question in general. So in general, the easiest possible case is that I'm at a leaf. If I'm at a leaf, the answer is going to be 1. How many leaves are there beneath me? Just me. If I'm at an internal node, though, I actually have a pretty straightforward way of answering this question. I'm going to delegate the answer once again to a couple of minions. The minions in this particular case are going to be child 1 and child 2 of the current node. As I move up the tree, regardless of how many total leaves there are in the tree that's beneath me, I could have 1,000 different leaves, but at the end of the day, I know that the number of leaves in the tree beneath me is equal to the number of leaves on the left plus the number of leaves on the right. So I can simply consult each of the 2 children. And what's nice about this and what makes it differ from Fibonacci is that as I proceed down through the tree, I'm not actually repeating any function calls. So yes, there is a branching, but there's no way that I'm going to call the same thing twice. When I move to the left child, I'm going to only consider the subtree over there. When I move to the right child, I'm only going to consider the subtree whose root is that child. So now I've got an idea. Remember, the easy case, what's going to inform our base case is going to be if I'm at a leaf. And I'm going to do the laziest imaginable thing, which is to say, our easiest case is that I'm at a leaf, in which case return 1. If I'm there, well, how would I know I'm at a leaf? I could make that check. I'm not going to make that check, though, because as I said, I'm doing structured procrastination. And so I will say, if it's the case that self.isLeaf is true, and we know we don't usually write equals equals true. So I'm going to be thinking about another method, which you can see here, which is going to return a Boolean value. So if that Boolean value returns true, and I haven't written that function yet, of course, but if it is true, then I simply want to return 1. I'll write that function momentarily. In the meantime, I want to think about my inductive step. And my inductive step says I have at least one child. If the left child exists, which we called child 1, if that exists, add its number of leaves. And if the right child exists, add its number of leaves. So I'm going to set a value or a variable called leaves equal to 0. At the end of this process, that's what I'm going to return. And then in the meantime, I'm going to say, well, if self.child1 And here's where I want to say, it could be the case technically that one of my children is just none. So I only actually have a left child or I have a right child. So in this particular case, if I just have child 2, but I don't have child 1, so I'm imagining I'm at an internal node, but I only have the right child. So if self.child1 is not none, well, I do have a left child, and add its leaves into the total. So the total number of leaves is going to get updated by adding in self.child1.count leaves. And this is not an else if circumstance. I'm going to make an independent check to say if it's the case that self.child2 is not none. So I have a valid right child. Well, I have a right child and add its leaves. So in most cases, I'm at an internal node. I'm going to have a left child and a right child. I'm going to look at what each of their total number of leaves is beneath them. I could have 400 leaves from the left side, and I could have 500 leaves from the right side. At the end of the day, I want to access each of those. I'm making a recursive call, and I'm adding in the number of leaves of each child, in their own subtrees, into the total number of leaves that I'm keeping track of. So a function that we saw previously as something that we really didn't have the context around solving becomes a function that's only like 8 lines long when you take the comments out. It says we have a simple base case where I know I'm at a leaf and I return 1, and otherwise figure out how many leaves you have coming from the left child, figure out how many leaves you have coming from the right child. If those exist, add them both into leaves, and then return the total number of leaves that you have coming from the left child and the right child combined. And that's it. The only thing that there is here to do is to also write my isLeaf function. But isLeaf is a pretty straightforward function to write. What constitutes a node being a leaf? And in this particular case, well, remember that a leaf is a node at the bottom of our tree. So if we look at our little example, it's A, B, and C. And what does that mean for those nodes to have a leaf? Well, it means if we tried to access both of the child references that we store at the given node, we're not going to get a valid value for either, meaning both the left child and the right child are going to be none. So we are at a leaf if both child references have that special value, none. That is easy for me to check. I know how to check if 2 things are true, and these 2 things are true if self.child1 is none and self.child2 is none. If that's the case, I return true. If we make it here, well, we have at least one child reference to a node. So I'm not at a leaf. And the default will simply be to return false. And the function is just that simple. Yeah. So I was double checking. If you can't get that R file, I'm sorry. You'll just have to check on a different browser or clear your cache maybe. I think that would be the way to do it, because it is there. If you follow that link, That is the updated UPGMA starter code in Python. So there is indeed an R file in the directory, but you might just have to follow me for now. Okay. Let's try going to main and ensuring that count leaves really exists. Because if you haven't seen a recursive function like this applied to something like a recursive data type, like a tree, it almost can seem like there's no way this works, right? Like the function is so short and everything is just being delegated to subroutines. Is it the case that this is just going to give us an answer? So I'm going to have this particular example and say, let me draw this tree. This is a tree that's worth drawing. So I'm going to say leaf 1 is equal to a node. And I'm not going to set ages just yet because I don't need to, but I'm going to set the label of that node equal to A. So if you look at our data types, so we have a label attribute and an age attribute of every node. If we don't set the age, it gets a default age of 0. We're not going to be looking at the age right now, but we are going to look at the label. And so I'm going to label this node A just so I can keep track of it. We're also going to have leaf 2, and it's going to get label equal to B. And leaf 3 is going to get label equal to C. Okay, so we've now declared all 3 of our leaf nodes. I'm going to declare internal 1, and I'm going to declare root. So I'm going to say internal 1 is going to be a node. And now here, I'm not so bothered about setting the label of this node. But what I will do is I'll make sure to set its children. So I'm going to say child 1 is equal to leaf 1, and child 2 is equal to leaf 2. So we have 2 attributes, child 1 and child 2 of the node. And now I'm saying they reference leaf 1 and leaf 2. What we have seen previously is that, and now I think this is starting to really hit home, is we're not going to, when we do something like this, I'm not setting child 1 equal to a copy of leaf 1. And here you understand why you wouldn't want that behavior. I don't want to be making a copy of the node that I've already made. I want to say child 1 should reference the leaf 1 node that I already created. And child 2 here should reference leaf 2. So this sort of reference assignment is exactly what we would hope would happen. And we're seeing that that's the case. Finally, I'm going to create one more root node. And the root node needs to point at child 1 equal to internal 1 and child 2 equal to C, which I called leaf 3. So I'll say child 1 is equal to internal 1 and child 2 equal to leaf 3. So now I've set the tree, and I could say, I could formally define a tree and say that the tree is the list of 5 nodes constituting leaf 1, 2, and 3, internal 1, and root. But I don't even need that in order to call the function. So I'm going to print the total number of leaves in the tree. And that's just root dot count leaves. Let's keep it on one line. I also should say, well, let's check some other things. Let's make sure that, I don't know, the number of leaves in the tree whose root is A is, and that's leaf 1 dot count leaves. And we should see, I would hope, that that's equal to 1. And let's say number of leaves in tree with root internal 1. And in that particular case, it's internal 1 dot count leaves. So we can see from the picture that this should print 3. This should print 1. And this third print statement should print 2, because there are 2 leaves in this subtree. there's 3 leaves in the overall. And then if I call this on a leaf, well, I should only have one that gets printed. So I'm going to save that. And then I'm going to cd into UPGMA, and I'm going to run main.py. And I see that the total number of leaves is equal to 3. The number of leaves in the tree whose root is A is 1. Good. And the number of leaves in the tree with root equal to internal 1 is equal to 2. So we could test this on larger and larger trees, but you can see that the logic appears to be working, which it is. Again, all because of like a 7 or 8 line recursive function that allows us to access some pretty deep aspects of the tree just with passing the work off to a left child and a right child. This is the culmination, in a sense, of everything that we've seen about laziness being good and delegation and subroutines being a good thing. Except the only thing that we're doing now is we're turning this idea of the subroutine back on itself and saying, I care about something about me at this node. Well, let me pass off the work to both my child nodes and ask them what that fact is about them and then combine it in some way. So anytime you have a structure like that, recursion is really going to be helpful. So even though we've delayed recursion until now in the course, there was a purpose of that, which is that a lot of times when recursion is introduced, it's introduced in the context of here is yet another way of solving the problem. And I very briefly introduced it that way when we talked about factorial functions or summing integers. Great. But at the end of the day, why would you write a recursive function to do either of these tasks if you can write a short function that uses a loop or that uses a single formula? You probably don't need to do that. In this particular case, trees show us that there are some contexts where recursion isn't just an alternative approach, it is the vastly superior approach for solving certain types of problems. We're now really essentially ready to run UPGMA because we did the hard work previously, as I said, of writing all of these functions. So we've produced the engine of UPGMA, and now we have count leaves. This implementation is finished. I hope it's correct. We have quite a lot of code here. So I presume there's a chance that some of this code is just terrible. It is my code after all. But if our code is correct, then our implementation is complete. There's just, as there often is, one little snag. And it's not that we've done anything wrong. It's that I could go call the function that I care about from IOUtil that I've already written to parse something from file, read in the tree from our data. We got tons of data here. And you'll notice, like, here's a hemoglobin data set. Here's a big matrix. Great. So we have the names of everything, and then we have a bunch of values. So this is one row of our matrix. And we're just printing the row. We just have the rows in the file. So this is echidna. The echidna says this is distance 0 to itself, and it has distance 46 to the goat, which is the next element, and it has distance 63 to the plumed whistling duck, and so forth. So the matrix values are all here. Awesome. I can grab all of these names, right? And then I can go and those will be my species names, and then I can parse out the rest of the matrix values. Then I can pass all of that information into the function that I wrote. I've got UPGMA from last time. It's going to take my distance matrix and the species names. You can see all that's in the file. Great. But then the problem is once I have the tree, all I have is a collection of nodes. So what do I do with that, right? Like, ideally, too, I would not have to sit here and figure out exactly how it is that I'm going to draw a tree. This is beyond anything that I would imagine I would ever potentially be interested in. And this is a very standard type of issue in like data science as a whole, which is that I have an abstraction of this thing that I care about, right? In this particular case, I have a tree, which is a collection of nodes. They live in a programming language as this collection of objects. What am I supposed to do with them? If I want to take a look at the tree, then I can solve a bunch of, apply this approach to a bunch of different biological data sets, but I actually just want the visual. So how do I get it unstuck? And what we've seen in the course is for certain types of questions, there's a lot of value in actually producing the visuals because they're beautiful and they're cellular automata. And I just need to make a grid and draw a canvas, and I'm just making a lot of circles or rectangles on the spot that corresponds to this matrix value. But this is like, I've got to draw a tree. So here is where kind of the general idea comes in of, I have an object. The only thing that I have to do is get every single person in the entire world to agree with me on what the representation of that object should be. And you'll remember that when we looked at object-oriented programming, before we transitioned to data classes, we looked at kind of the raw way of defining your own user classes in Python. And there's a function that you usually needed to write called REPR. So I think we saw this when we looked at shapes. So when we looked at shapes, we had moved to data classes. So I don't know that I have my old representation. Oh, we do. So we have a class rectangle. And we had to write init, but then we also wrote an REPR function. And at the time, you weren't thinking about it this way, but what we were taking was like, we have an abstract concept of a rectangle, and then we're going to print it to the console. So this is nice. We're going to tell the user, I have a rectangle, it's got a certain width, it's got a certain height, these are its other attributes. The problem actually is the same here, because what REPR is doing is taking an object that might be complicated, and then it's converting it into a string so that it always has the same format. What we're doing is just a more complex version of that, which is that now, I have a tree and I need everybody to agree. So our tree here is a list of nodes. I'm a little worried by the fact that I had something red here, but I think that's okay. This appears to be okay. Okay. We have a tree, which is a list of node objects. And if that's the data structure that I'm working with, then the question becomes, can every single biologist in the world agree on a string representation of a tree? And that might seem like a really hard thing to do. I mean, what I'm getting at here is the problem of file formats, right? That what file formats are an agreed upon way of representing something. And we are fortunate that we live in the 21st century where everybody has already kind of agreed on certain file formats that are involved with trees. So there aren't 6,000 different file formats. And the one that we're going to use is called Newick's file format, or Newick format. I'd be impressed if anybody out there watching this happens to know why it's called Newick format. Kind of like the most famous file format for trees. Yeah, or I guess I just added a breakpoint. Yeah, good. Okay, I guess I clicked in the margin. Thank you. Any guesses on why it's called Newick format? In the meantime, I will show you the Newick format for an example tree. So we have our sample tree from before. The Newick format for this tree is A:3, B:3 in parentheses, :1, comma, C:4, semicolon. And that might look really hideous to you. And you might think, well, that's going to be challenging to take a tree and then produce this format out of it. My goal is to make it hopefully seem, if not easy, pretty straightforward as to where this format is going to come from and why this thing is going to represent what we think of as this tree, which is that there's a root with age 4. It's connected to a leaf node on this side. It's connected to an internal node on this side with age 3. and that node in turn is connected to two leaves called A and B. It turns out if you just gave me this format, I could reconstruct this thing. So I can go in this direction, but also backwards. And so this is a nice, tight string representation of the tree. A lot of the times when you come up with something in science, probably the smart thing to do is to either name it about yourself or to get somebody else to name it about yourself. The biologists who came up with Newick format, and maybe they didn't realize just how fundamental it was going to be to representing evolutionary trees for decades, but they named it after where they were having lunch, which is Newick's Lobster House in Dover, New Hampshire. I was very fortunate a couple years ago to have a student who had actually been there and could report back on the food quality, as well as the fact that I don't think that lobster house cares that this very foundational tree format was named after their restaurant. You think that maybe there might be a plaque or something like that. I don't want to pass incorrect information on. I don't think it's on their radar to celebrate the history of Newick format at this restaurant. And that's a shame, because if they were big recursion fans, they'd probably buy a big plaque. And you're saying, well, what does this have to do with recursion? And the answer is that it has everything to do with recursion. So I might just copy my sample tree over so we can take a look at it in data types. But I have a little function, that's one more method that's lurking here, that's called toNewick_ages. And I'm going to take self as the parameter here, and it's going to produce a string. So it's, like I said, it's like REPR. It takes something and it produces a string, except it's taking a node. So it's like a node method. This is living inside of the node class. And what the string that it's going to produce is the Newick format for the tree whose root is at the current node. So I'll come down and copy that so we can look at it as we go. And I want to think through this. I want to think, well, I remember there's really only one trick that I have. If this is going to be recursive, if I'm at an internal node, then I need to look at the left child and the right child. And if I'm at a leaf, then I need to look at something else. And you know what? I bet, the other thing I'm going to do is I'm going to ignore this semicolon just for a minute. I'm going to ignore it just for a minute. But I bet that the easy case is that I'm at a leaf, okay? And so I will say, I want you to imagine that the tree were just a node C. And I wanted to say, what's the Newick format of just this node? It's just one node in a tree. What's its Newick format? And if you wanted to email somebody and say, here's the Newick format of this particular tree, well, notice here, what I'm representing is, you might see these are edges. So when I say A:3, B:3, I'm representing these branch lengths. So this says B is connected to its parent with 3, A is connected to its parent with 3. Notice C is connected to its parent with 4. But if my tree were just a leaf, well, in that particular case, this is very easy. The tree would just be C. So that's how I would represent it in Newick format. So I'm going to look at this as, the base case is just if self.isLeaf. I get to reuse my method to say if I'm at a leaf. So the base case is I'm at a leaf, and the Newick format is just my label. So if I'm at that leaf, I'm simply going to return self.label. So far, so good. So this is me. That's the entire tree. And so the tree beneath me is just C. Same thing over here. It would just be B or A. So then I need to say, well, the inductive step, if this works, I need to access the left child and the right child and combine them in some way. And for me to understand this, what I would do is I would just look at the easiest imaginable internal node. And the easiest imaginable internal node is not the root. I don't want to think about something that has 470 kids this way and 500 the other. I want to think about something like internal 1. So internal 1 just has 2 children. So if this were, and they're both leaves, if this were the tree, then I want you to notice I could represent this entire tree with just this part of the Newick format. So I could say A is connected to its parent with a branch length of 3, comma. B is connected to its parent with a branch length of 3. And this would represent the tree. Okay, so I want you to keep that in mind. So let's say the Newick format of the internal of the tree whose root is internal 1 is A colon 3, B colon 3. And the format itself is kind of defined in this clever way so that a pattern will emerge as I go up the tree. Because when I'm at the root and I look to the right child, okay, I want you to notice the internal node says look at the left child and its branch length, and then comma, and then look at the right child and its branch length. The whole idea is I'm just going to keep applying that idea upward. So when I look at the root and I'm going to say what's its left child, well, by left child I mean it is the tree whose root is internal 1. So what did I say that was? It's this. So the left child is this. And you see it got highlighted up here too. So I have A colon 3, B colon 3. That's the left child. The right child is C. And note, the left child has its branch length of 1. So that's the one that I see there, comma, C colon 4. And so even though I'm moving up, in each case, in either of these cases, the idea is take the Newick format of the left child, and I'll just say, we put this in parentheses, say what's the Newick format of the left child, colon, branch left, and then we're going to say Newick format of right child, colon, branch right. I couldn't fit that on one line if I tried. And then close parentheses. So Newick format of left child is just go into the left child and access, 2 Newick ages. So I can get this format just from saying, if I make it here, I'm at the inductive step, because otherwise if I'm at a leaf, I would have already returned the label of that leaf. But in this particular case, the function's actually going to be a lot shorter than you might imagine. Again, because I can kind of brilliantly apply recursion. So I'm going to have 2 strings called left and right. I don't even think I need them, but they're going to represent, what's coming from the left and what's coming from the right. I'm also going to do a little bit of pretty formatting to make sure that it gets displayed right. But, if it's the case that self.child1 is not none, then I'm going to set branch length 1 equal to self.age minus self.child1.age. And if I were being very persnickety, I would set this equal to the max of that and 0, just so I don't have any issues with this being a negative value. I don't think Newick would like that, but let's just assume our data are okay. I think it's just clearer to say the branch length I care about is my age minus the child's age. So in this case, this branch length of 1 comes from an age of 4 here and an age of 3 here. That's something we've seen from UPGMA, but even if this is the first time you're seeing that, you can see it's just the difference here. And I'm going to also do the same thing for if self.child2 is not none. Okay, so if you look at the right child and you see something, well, branch length 2 is also going to be self.age minus self.child2.age. Make this a little bit nicer. So those branch lengths are important. We know that. And in either case, what did we say? The idea is we take the Newick format of the left child, colon branch left, Newick format of the right child, colon branch right. And so the left string now is going to be really just self.child1.to Newick ages. Okay, so that is the Newick format of the left child. And then I'm going to append to that the colon, and I'm going to append to that branch length 1. And I'm going to do the same thing on the right, except I'm going to change it to right, and I'm going to change that to self.child2.to Newick ages, and then have a colon, and then append the second branch length to it. So at any point in time, I'm going to take, this is Newick format of left, colon, branch left, and then I need a comma between them, but Newick format of right child, which is here, and then the colon, and then the branch of the right child. So that's all really nice, and then the only thing that I have to do is make sure that I have the comma, make sure that I have the parentheses on either side, and so at the end of this process, I'm going to say return a parentheses plus left plus a comma plus right plus a close parentheses. And that would give me my Newick format. And it's pretty impressive. I mean, look at how short this is. You look at this thing and think, I'll never understand it, right? And yet I can take any tree, regardless of whether it's got 1,000 nodes in it or 1, and it's always going to have some Newick format. And if it's got a lot of nodes, everything here is produced as the result of recursion, which I think is pretty cool. I will also make this a little prettier. Like, I like this, but probably the absolute best way of doing this is with something like an F string. So I'm going to have the F string, and I'm going to put left in there, comma, right in there. Okay, and I'm probably going to do the same thing over here. You know, I could also update these with F strings, because the F strings also will allow me to do things like format it. So I could say demand that the branch lengths are always to 3 decimal places. I think I'm going to do it to 6 decimal places. So I'm going to say left is an F string, and this is going to give me the same exact result, but I'm looking at this as a variable. So self.child1.to Newick ages, I'm putting that in braces, and then I won't have this as a concatenation anymore. I'm just going to say colon and then branch length 1, and then I'm going to say do that to 6 points of precision. And I think, what am I missing here? I think this probably needs to be, yeah, like that. Okay. And I'm going to do the same thing with the right. So F as a string. This is going to be like that. And then I need to put that that way. And then the colon just gets added in. And then I add the branch length like that. And this is to 6 decimal places. All that's boring. It just allows me to have this, you know, specified to the number of decimal places I want. At the end of the day, it's going to be the same result. Now I have a way of like taking this tree and then converting it into a string. So let me make sure that that actually works. That's probably something that would be an important thing to do. So when we look at our demo here that we had before for our sample tree, the next thing that I want to do is to say, well, if I print Newick format of tree, you know, does it give me what I want? And what is the Newick format of the tree? The Newick format of the tree is just to say access the root, and the root is going to say root.to Newick ages. And here we're going to, you know, cross our fingers and then run our code, and ooh, something bad happened. In this particular case, nothing bad happened. It's just that I didn't set any ages. So I forgot. I got ahead of myself. I was so excited about file formats that use recursive functions that, for some odd reason, that I forgot to actually set the ages of the two internal nodes. So let's make sure I do that. So the internal node 1 is going to be age equal to 3, and the internal node 2, or the root, is going to be age equal to 4. So now when I do that and I'm going to run it again, here's where we see we do indeed get the Newick format that I care about. So A:3, B:3, all in parentheses, :1, comma, C:4. There's just one little very annoying thing, which is Newick format usually demands that we end this with a semicolon. And if I try to add, a semicolon here, like that would be such a reasonable idea, right? But the problem is then that's going to happen multiple times. So it's going to try and add it in internally as well. It's like anytime I'm at an internal node, I'm going to add a semicolon. So yuck, right? And the fortunate thing is that I went ahead and kind of fixed this issue for you. So if you look at IOUtil, I have a function called toNewick that takes a tree as input. And all it does, this looks hard, it's not. All it does is it goes in and says, if we're assuming that the root is the last node in the tree, which is how we're going to work with this. Okay, so I'm going to have a list of nodes. The last node that we ever look at is going to be the root node. So tree of -1 is the same as tree of length of tree -1. Okay, so a little negative indexing, that'll mind this sometimes. But we go in and we look at the last node, that's the root, convert it to Newick ages, and then just add a semicolon to the end and make sure that you've got your parentheses on either side. So that's the only thing here that's really missing. And now when I run this again, I could fix this by just lumping all of these nodes into a tree, meaning a list of nodes, and then call that function on it, and I'd be good to go. In this particular case, I'm going to say this is a sample tree. And so all that code is just going to go into a function. I will simply call this function I mentioned in IOUtil toNewick. And it's going to call the function that we just wrote. So it's going to call that method, but this is just going to tie all this together. All right. So we are ready to run the whole thing. And then we're going to be ready to run this on data. So don't go anywhere for now. What I want to do is take 2 command line arguments. It's actually going to be kind of some easy parsing here. So we will have 2 command line arguments. And this is going to be like, where is the input data? And where should we write the Newick tree? All right. So the input file that I care about is going to be sys.argv of 1. Remember, sys.argv of 0 is always like the name of the program. Then we're going to have the output directory, and that's sys.argv of 2. And, at this point I'll say, let's print and say command line arguments read. Reading in matrix from file. And once I've done that, I can say, species names, and the matrix that I care about are read matrix from file, input file. And I'm missing some things. So Python's angry at me that I haven't imported sys. We probably should do that. It's angry at me that I didn't import read matrix from file. And so that is a function that is contained. If we look at IOUtil, we've got a read matrix from file function here. Takes a file name. Good. Returns a tuple of what? list of strings, that's our species names, and then the distance matrix. Okay, all that's specified. I hope you see, as an aside, just how useful it is to have doc strings and to have type hints in Python. Like, why would you not type this out? It just makes it so easy to understand. What does this do? Oh, it takes the name of the file, that's a string, and it returns the two things that you care about. What is that? A list of strings and a distance matrix. The good news is AI codes well. So if it replaces all of us, it's no big deal. But we're going to say from IOUtil import read matrix from file. Okay, so now that's going to be good. And if we make it here, I'm going to say data read. That's a good thing. And then we look at our functions and we have UPGMA. What does it take? It takes a matrix and it takes the species names. So I need to make sure I give it these two inputs. So UPGMA is going to come from functions. And I will say at the end of this function, what am I going to produce? I'm going to produce a tree, which is a list of nodes. So I'm going to say that the tree that I care about, let's call it T, is equal to UPGMA of, and remember, UPGMA takes the matrix first and then the species names. So I'll say MTX and species names. And now I've got the tree. And one thing we might do, actually, I don't have the command line arguments yet, so let's hang on now. It's going to say we could run this on an example, but there's no need here. So the point here is, now what are we going to do? We are writing the Newick format to file. So I need to know in the output directory, where am I going to go? And here's where we're going to just do just a little bit of faffing with the variables and making sure that we're parsing everything. So if you look at the data folder, we're going to pass in the data folder or the input directory as like data / citation / the matrix that we care about. And we have notes here to indicate, this comes from, for example, a bunch of real DNA, it comes from a real place. And the note explains how we computed this. But at the end of the day, we care about the matrix. So that's going to be my first parameter, is data / citations MTX. That's a lot. But then when I write this to output, I want to write it to just output / maybe citations. And so when I go into main.py, I can do this by saying, what's my output file name? It is equal to, I'm going to take the input file and I'm going to call path on it. Okay, so path here is going to take this input file, which could be really long. It's going to be like data / citation / something. And it's just going to trim out the start of the file and the file extension. So it's just going to go in and it's going to get the file name, which is citations. Good. That's good. It's going to get rid of all that initial stuff because I don't want that initial stuff. What I want is I want to take that and then I want to say plus dot nwk. Okay. And then I'm going to say write Newick to file of the tree. And here's where we're going to look at IOUtil. We're going to say this is the function that we talked about. It takes a tree. It takes where you want to put it in terms of the folder that you care about. And that is our output directory. And then it's going to take the file name that you want to write. So in this particular case, I need to go in and say, I also want to import that particular function, which is called write Newick to file. And once I've got that, that's imported. And so I'm going to take the tree, in this case I called it T, and it's going to take the output directory, which the user specified. So I'm going to write it to output. And then I'm going to give it the output file name. All right. And I think I need to import something here. So in this particular case, just checking. Yeah, it's from pathlib. So there's one more input or one more import. So in order to use path, I need to make sure that I go into path, this path library, and import path. So it's just going to make the input output a little bit easier. And when I access that, it's taking that path and then getting the stem. So I want to make sure that I access just the name of the file without this full input directory associated with it. So that's what I'm doing when I say path of input file.stem. It's going to go in and just get the file name itself and not even have the extension. So I'm going to add .nwk to it so that when I look into the data and I'm looking at like giant panda bears and I've got giant panda bears dot matrix, the only thing I'm getting from this is just giant panda bears. So that's convenient. All right. Now, then I will write this to file. I'm going to have the Newick format. And once I've done that, you know, at this point in time, I'm finished, right? So I'll just say tree written to file and exiting normally. Okay. And if we've reached that point, we should be pretty proud because we've done quite a lot. We've implemented all of UPGMA, and then we've also written this to file using our Newick format. So let's hope that works, is our only thing. So I keep adding breakpoints. Right? The only thing there is to do is to then try this. And I mean, there's a little bit of cleanup I probably should do. I should make sure that I'm not, if I look at systa argv and it's not equal to 3, I'd say, raise a value error and say, incorrect number of command line arguments given. Okay, so that's the type of thing I would do. So if we want to run this, Python 3 or Python on a Windows machine, what file do we run? Main.py. So that's the first argument. And then we have two more, indices 1 and 2. And the first one that we're going to pass in is the file that I want to produce or read in for data. And so for data, if I were going to look at citations, we're going to say data / citations.mtx. That's our input directory that I care about. So I can go in and look and say, here is, it's not a very big file, but it comes from real data. And I'll explain what that is here momentarily. But the idea is it's a distance matrix, and it's going to access, this is a bottlenose dolphin and a killer whale and a blue whale and so on. We're going to read in those species names. We're going to read in the matrix itself. And then UPGMA is just going to run behind the scenes. So at the end of that process, there's only one other thing to do, which is to specify what's the output directory that I care about. And the output directory is, I'm just going to put it in output. So that was the nice thing about doing this path thing, was that I'm just going to tell it, look, just make me something called cetaceans.nwk and put that in my output directory, which is currently empty, as is this images directory. So here is where we just need to run this and hope that UPGMA works and hope that I don't have a bug. Oh, I keep hitting enter in the file. Okay, let's try that again. Failure to launch. All right, this is why I can never be an astronaut. Okay, no such file or directory. That's an easy one. All right, data/cetaceans.mtx. Now, in my enthusiasm to run this, I missed the fact that it's not in data/cetaceans.mtx. There's this intermediate file or intermediate folder. Okay, so that should be easy to fix. When I run this, it would be data/cetaceans/cetaceans.mtx. All right, now I close my eyes again and run it again. Okay, so UPGMA has finished. Hooray. As a result of this, and I could go and test all the functions and plug them into our auto graders that we have for you, you know. But in the meantime, let's take a look at what actually got produced. So we're going to go to output, and hopefully it's not like everybody's a 0. That would not be good. And now we have something that looks, I mean, this looks good, right? There's one semicolon at the end. That's good. There's a bunch of parentheses. There's branch lengths, and they're different values. So cool. The only problem is I've got a file format. I just need to have something, you know, one person in the entire world needs to know how to take a Newick file format and convert it in and make a nice pretty tree for us. Before we do that, I'm going to run everything else that we might want. So, you know, we're going to put everything in the output directory, but there's a bunch of other examples that I want to run. I want to run giant panda bears / giant panda bears.mtx. Okay, and we're going to see that occur in the output here. And then I'm just going to do this same thing for each of our other examples. Cytochrome C is an old one if you see that. So we're not going to do that, but we're going to do great apes. Okay, this is going to be long, but you know, this is in the great apes / great underscore apes. Not a fan of that right after we used a hyphen, but it's all right. We only need to do this once. And then I'm going to do HbA1. So this is a hemoglobin data set for a lot of different animals. We're going to do hemoglobin.mtx, and that one works. And then I'm going to do HIV subtypes, and that's going to be in an HIV subtypes folder, and HIV underscore subtypes, HIB. Okay. All right. And then we're going to have 2 more mitochondrial haplogroups, I think I called this. Yeah. This is a spelling practice test for me, and that works. And then we've got one more, which is a bunch of SARS-CoV-2 data from the UK. So I'm going to have something that's shorter here. And I'm just updating data to be data /UK-SARS-CoV/2. And then inside there, this is called SARS spike. So this is a bunch of comparisons of spike proteins from a lot of different viruses taken from patients. and then we're going to run that one. Okay, so at the end of this process, we've got all our demos ready to go. You have one for giant pandas and bears. You have one for great apes. You have one for hemoglobin for a bunch of animals. You have HIV subtypes, and there's also some simian viruses in here too, so viruses that come from like chimps. And we have mitochondrial haplogroups, so this is a human data set, and then we have a viral data set here as well. So there's a lot of zero values here if you have two patients that wind up with the same spike protein, so that's not uncommon that you would have people that have a virus that's essentially the same. So all of that now is written to file. And the only problem is we have to ask our one person who has ever made a visualization based off of Newick format. So this is where R is going to come in handy. And I remember I saw Roy say earlier in the chat something about R, that you're excited that you get to see R. And I'm glad of that. I'm going to give you my take, which is R is great. I love R. You know, if you follow this, you know I hate Python, but I love R. But I love R on like very conditionally. The way in which I love R is that R will basically make any kind of visualization you want in whatever way you want it to at this point in time. And also, it is so unbelievably boring to actually type out anything in R. I mean, I've done it. And I've looked, the old way to look at like learn R was you would just have like sheets and sheets of commands that you might use, but that you probably wouldn't. And all of that has just gotten obliterated by AI because you can tell AI exactly what you want and gives you the R code. And if you want to change it, you just tell it exactly what you want again. So as long as you can clearly specify, hey, I've got some Newick files from trees. I would like you to produce some nice visualizations for this. AI will just yawn, roll over in bed, and do it all for you. So my take is there's no reason whatsoever for you to ever open up RStudio and open an R file and type literally one symbol ever again. As long as you have an internet connection and enough AI, the problem has been solved. And R's purpose, which is to make some pretty pictures for us, has been completely resolved. And that's nice because it allows us to make demos that are very, very long, you know, and pretty. And typing all of this out myself would have been something that would have driven me to the brink of madness. But with AI, it's just kind of done. And I can just say, I'm going to take all of this code, I'm going to just select all of it, and I'm going to just click run, and it's going to go through, and it's going to make all of my images for me. And at the end of the day, it's probably always going to give me warning messages because this is R, and there's always warning messages. And that doesn't mean that there's anything wrong. It just loves giving you warning messages. But after this process, you can run that entire pipeline. It's all done in the blink of an eye. And I'm going to get some pictures. So here's where I get to see some cool pictures. We can start with something like great apes. So why don't I take a look at this? We will start with simple trees that give us results that are perhaps not earth-shattering. The first one is we formed a matrix from great apes, and then we've added some other things in here too. So we have a mouse and we have the zebrafinch. The data that we're using is mitochondrial DNA. The idea here is mitochondrial DNA, you know, the mitochondrion being and I know what's going through your head because it goes through everybody's heads. Everybody has been brainwashed effectively by their biology teachers to fill in the blanks and say the powerhouse of the cell. But we also know that mitochondria have their own genome. And, you know, regardless of kind of what happens inside of your own cells, there's not necessarily a lot of selective pressure that's being exerted on that mitochondrial DNA. So there will be differences that arise as the result of genetic drift when we look at, say, our mitochondrial DNA against that of a gibbon or an orangutan or so on. And that's nice. So it means that there's sort of like, presumably there's this molecular clock. If you did our reading associated with this on programmingforlovers.com, it talked about that UPGMA is powered by this notion that the pace of evolution is kind of the same on every branch. And if you make that assumption, which is kind of a strong assumption, but if you make that assumption or you're working with a data set where that assumption makes a lot of sense, then you get good results. And so here we see, like, we have reasonably good results. And this collection of 3 organisms, at one point in time, I think it probably wasn't 100% resolved, but most people, I think, believe that we have bonobos and chimps here, and then we're kind of separate from them. So their most recent common ancestor diverged later than the most recent common ancestor of all 3. So the evolutionary tree here is the powerhouse of like producing nice visuals of evolution. And all we should do is, look at a few more complex examples. So there's nothing earth-shattering about the great apes. If we look at our giant panda data set, however, this looks like also a pretty simple picture. But this is a data set or a tree that corresponds to a collection of bears, a couple of different species of pandas, and then we also have as additional species, we have a raccoon and a ferret. And there was a long period of time where this was actually a dispute among biologists. And here it's a classic case study example of how the transition to a molecular era kind of slammed the door shut on what at one point in time was a debate, because now we have mitochondrial data from all of these different species. We can just grab all their DNA, come up with an approach to make a distance matrix, and once I've done that, produce the tree. And what's nice, you get an immediate conclusion from that tree, which is on this side of the tree, you get the raccoon, you get the ferret, and you get the red panda. At one point in time, some biologists thought that the giant panda should be over on this side of the tree with the red panda, and that it should be similar to a raccoon. But then when they sequenced DNA, plug this into an evolutionary tree construction algorithm like UPGMA or others, they found the opposite to be true. So they found that the red panda is indeed similar to a raccoon, but that the giant panda is more similar to bears. So its most recent common ancestor with bears is more recent than if you go farther back in the tree and find the most recent common ancestor with the red panda or the raccoons. So here is a classic example of calling two things the same thing, a panda in each case, but the giant panda belongs on the bear side of the tree and the red panda belongs on the raccoon side of the tree. We can look at hemoglobin. So the next thing we might do is, why don't we do this for a bunch of animals? And it won't be a surprising picture, but I still think it shows the power of what we're doing, which is to run, like, we're running an algorithm at scale. So at this point in time, you can't even see anything. So I'm going to zoom in on the legend here and say all of these, they have the Latin names associated with the organism, but then they also have a common name. So we have a Coscaroba swan or a Cape Barren goose or a marbled electric ray and so on. And we've color-coded these. Yellow are mammals, blue are birds, green are fish, orange are reptiles, purple are amphibians. And we can see that, in this particular case, and this was just a data set that for whatever reason was very goose and swan heavy. This data set just liked geese and swans. But what you see is an evolutionary tree where, as you might expect, a lot of things cluster together that are related taxonomically according to how we might imagine them to be. So here's where you have all the mammals after we got through all of the birds. But notice, well, there's something to be learned here, which is, or at least something to be explored, which is that all these geese and swans are related to each other, But notice that, there were some other birds that kind of clustered over here, also with a tortoise. So the question is that an artifact of our data? Is our algorithm performing poorly, or is it something that's genuinely worth investigating? Notice all of the mammals are clustering here, and I think we're in here too. Yeah, so we see chimp, bonobo, and human. Same picture as what we had before. So this is sort of like the great apes are lurking in this area, and we've zoomed out from this, and we're seeing something that applies to a lot of different animals. So we come up here and we see the fish, right? We can even zoom out and see, well, the fish appear to be the least similar to anything else in the tree. We only have a few amphibians here, but they're on this side of the tree with the birds. And then we also see that the birds and the mammals share a recent ancestor around here after we've seen the separation from reptiles, fish, and amphibians. So pretty good. We're reconstructing kind of how we've thought about taxonomy for a long time, but now we're getting a nice crystal clear picture from this. And we're also getting some places to look to say, could our algorithm be better? Are there areas of this that might be more interesting to study? Again, the reason why this looks so clean is you have genetic drift. You're looking at something, hemoglobin, that in all these organisms is carrying oxygen through the blood. And even if there are changes to it on the level of sequence, meaning its protein is changing a little bit in terms of the amino acid constitution, when you look at the final result of the protein, it always looks the same. So you can have mutations, but those mutations are producing a final result that winds up essentially serving the same function. So we're seeing the result of drift or just random collections of mutations accumulating over time. And that's helping us differentiate these species. Remember, if we have that happening, then UPGMA might be a good approach because it's assuming this equal molecular clock on every branch. If we look at HIV, here we have another classic case study evolutionary tree. So at one point in time, it was believed, and I remember as a child myself, it's what I was taught about HIV, that there was one point at which one human was infected with HIV, and that was like a patient 0, who then was the initial patient in the pandemic corresponding to HIV. When you sequence the DNA or RNA of a bunch of different patients who have HIV, and then you compare that against viruses that we can see that are simian viruses, the story becomes a lot murkier. So you have these two main groups of HIV. You have HIV-1 and HIV-2. And notice how they're on completely different sides of the tree. So we've colored those blue and red. And you can see that this HIV-2 is more similar to this SIV that we have in this manga bee, that by far, than it is to anything on the other side of the tree. And even on the other side of the tree, this particular HIV is more similar to this simian virus than any of these viruses. And then you have another location up here where you have a couple of SIVs that are more similar to this HIV. So what you're actually seeing, the only way for this to be true, is if HIV is leaping from animals to humans at multiple different points. This actually is part of the reason why HIV has been so notoriously difficult to treat and to vaccinate against, because what we know of as HIV is actually a constitution of a lot of different families of related viruses that have all made this transition point towards humans at different points in time. And now we can see this picture, right? At one point in time, this was a pretty substantial biological result. And it all comes from the fact that we have high-powered algorithms and we have nice molecular data where we can make rigorous studies of them. We can finally, well, not quite finally, but we can look at the SARS spike protein. And I've made the leaf nodes extra large here so you can see an immediate conclusion, which is the only thing that I did here was produce a distance matrix from spike proteins taken from UK patients the viruses in UK patients over 5 years of SARS-CoV-2 outbreak. And if we color them according to the year, then you can see, as you might expect, that there's a lot of clustering based off of the time. It's of course not perfect, but when we zoom in, and we can see this, we see in 2020, these are these light blue. So we weren't actually able to sequence a huge number of different viruses from patients in 2020, but for the next 4 years, there was a lot of viral sequencing that happened. 2021 is green, and 2022 is orange. 2023, I believe, is red. Yeah. And 2024 is purple. So this was when we stopped collecting data. But the other thing that to me is fascinating about this is in the earlier days of the pandemic, you see 2020 has very, very similar species. There's not a blue point that's not very tightly related to each other. I think there's a later point in 2020 where what you're seeing at this point in time is a transition from one variant to another. So there were some viral sequences that were obtained that correspond to this particular variant of the virus, and these are the sequences that were obtained from another one. So at the end of 2020, I presume what you're seeing here is the transition from one variant to another. But the other thing that you see when you zoom out further is, well, all of that tends to cluster in a pretty small part of the tree. So these were the early days of the pandemic when the virus had not had enough time to mutate very much. And so as a result, it was easier to vaccinate against because every genome of every virus that was in the human species, in our reservoir, so to speak, was actually very similar to each other. The more different the virus has gotten, the more challenging it's become to vaccinate against. So for that reason, you can see that here where this part of the tree is just 2020 and 2021, but when you zoom out, you have, a much wider diversity of organisms because the most recent common ancestor of everything is back here, and we can roughly say that this distance on the x-axis corresponds to how different two of these species are. So it's quite a bit larger, and we see that this increase in variation occurs as we go. Nevertheless, we also see a lot of clustering. So there's an evolutionary process too that's also forcing all these different viral sequences to cluster together and be similar. So this I think probably corresponds to a variant. This is another variant from the same time period. We have another variant here and then another variant here. So even though the virus is evolving as it's spreading through the population, it's becoming more distinct, there's also this process that is constituting like a bringing back together because a virus with this specific collection of mutations happens to be more fit than others. And so there's also this clustering effect that we still happen to see. All of that is coming just from looking at the picture of forming the tree. But there's one more picture that I want to show you, which is, that's a really good one, which is taking the mitochondrial DNA from humans. Because in humans, mitochondrial DNA, or in any organism, mitochondrial DNA is inherited essentially without changes and without paternal DNA incorporated via a maternal line. So unless you have incorporated, a mutation along the way, your mitochondrial DNA, the DNA that's in all of your mitochondria and all of your cells, is largely going to be just your mother's mitochondrial DNA. And so as a result, the mitochondrial DNA is sort of a record, in a certain sense, of the migration of women around the planet. And so when we reconstruct that and we take individuals of known ancestry or known ethnicity, and then we produce the evolutionary tree from their mitochondrial DNA, we get a picture that is, really impressive. So here, we separate out individuals from different regions. So we have, green individuals here are Native Americans, but we have also like Eurasian individuals and African individuals and so forth. And the picture that we see, so this is like the blue color here is East individuals, so it would be Oceania, East Asia, South Asia. You have a Siberian sample and so forth. So notice, though, that you have European samples here as well as a couple of Native American samples. And the real out of Africa tree or real mitochondrial studies might incorporate hundreds or thousands of individuals. But this is a nice small illustration of it, where you can see, we have our Eurasian individuals, and they're all sort of clustering together. And then when we zoom out a little bit, we get, these East Asian, Oceania individuals too. But you'll notice that they're peppered in also with African individuals. But when we zoom out, we see these African representatives occur, across the entire tree at a lot of different points. And so this at one point in time was just an immense scientific achievement, right? Because what it was saying is if you sequence the DNA and you're measuring, you're looking at the genetic diversity, especially on the mitochondrial level of African individuals, you see a greater diversity on the continent of Africa than you do if you look at the entire planet outside of Africa. And so this gave an immense amount of molecular evidence to the hypothesis that although people are in Africa all descend from somebody like about 200,000 years ago, and we go back and we look at the clock, everybody who is migrated outside of Africa, or it descends from somebody who has, that transition point was only about 60,000 years ago. So we need a lot more individuals to fill out this tree in order to see that. But you can see in this particular case, the fact that there's a lot of diversity among the African individuals, but also the fact that they date back to a more ancient, recent ancestor of everyone in the tree. Okay, so all of this is coming from data that was easy to get. That's the beauty of this era, is all of the data that we relied on here is publicly accessible. So some of it was a little more challenging than others, but it leads us to a lot more questions. That's the great thing about science. And one of the, I think, themes of what this class is all about is we answer one question and a few other questions pop up. In this particular case, I've even hidden a couple things from you, right? So, one of the things you should ask me is exactly how was it that you formed this distance matrix? And we have a note about it, but maybe this interests you to say, if we're looking at this particular distance matrix, or we're looking at our giant panda example, or whatever example that we're looking at, we got these distance matrices, but how? And we got these DNA sequences that come from a database somewhere that says, this is the mitochondrial data of all these different organisms. And it's a big file of ACs, Gs, and Ts, but how did we get that, And where are these genomes coming from? When we make this matrix, are we making the matrix in a way that's good? What does it mean to make a good distance matrix? Like when we say that this value here between the giant panda and the black bear is 0.186627, like how do we validate that to say that that's a reasonable value for this? And that when we look at the distance to the brown bear, it's 0.179035. Why is that a reasonable value? What approach is good? How do we compare these? And in which particular context would I apply one distance approach versus another? All these questions are why you should probably take computational biology with me, or you should check out our bioinformatics algorithms book. But there's just one more story that I want to tell. And that's one thing that we didn't do was the cetacean data set. And I'm going to show you it for a reason, because it's yet another, I'm in the wrong place. It's yet another example of something that at one point in time was a novel idea, not that long ago in biology, because we had access to molecular data. So here is our cetaceans picture that we formed from a data set involving the organisms that are shown here. So things like, we have dolphins and whales, but we also have a camel, an African elephant, rhinos, and so forth. And in this particular picture, we have that the hippo is closest to the cow and the giraffe. And there's only one problem with that, which is that that's not what biologists believe to be the case. I produced something with R that I didn't tell you about. So there's one extra picture here. And the one extra picture that we have is going to show this tree alongside another tree. And I'm going to show you that tree. It's here on the right. And this is a tree formed from a different evolutionary tree algorithm on the same data. So we have the same data set, the same distance matrix. But the tree on the left is what UPGMA produces, and the tree on the right is what something called neighbor joining produces. So when you ask this different algorithm, neighbor joining, the answer that you get is that, well, the hippo does not belong immediately next to the cow and the giraffe. Actually, where the hippo belongs is in this part of the tree here, which is alongside whales and dolphins. And this is generally what biologists believe to be the case. This was a surprising fact that the hippo is the closest known land relative currently living to whales, which is maybe not very complimentary to the hippo, but is nevertheless what most biologists believe. But if you look at, comparing this tree against the tree that UPGMA produced, now we start to become a little concerned because we had a conclusion from the same data that's led us to something that is not what most biologists believe and is not the result of what happens when we produce take a different algorithm on the same underlying data set. The answer here is that UPGMA is just, unfortunately, not the best algorithm. And although it's able to reproduce a lot of biology that I've shown you, there are certain instances where it's going to get outperformed by other evolutionary tree algorithms. So if you want to investigate more evolutionary tree algorithms and figure out why is this the case, what makes one evolutionary tree algorithm preferable to others and in certain contexts, to get that answer, you're also going to need to take my computational biology course. So I'll have you check out Great Ideas in Computational Biology, because you might be wondering, how is it that neighbor joining works? Well, you'll have to join me for that. That's going to be it for now. We've covered a lot with object-oriented programming and trees. We're not done by any stretch of the imagination. We have a lot more to go. But we're going to have to save it till next time. So I'll see you then. And until then.